Hey, AP Chem. Today we are going to be talking about moles of gases. I've been doing kind of a lot in the last start of the unit that is related to kind of pressure and volume and temperature and conceptually how particles interact, but I've kind of been avoiding moles of gas. And I think that's because you've got to get a good idea of kind of how everything works without getting too caught up in the weeds of the numbers. But today, we're getting into it, and we're going to be talking about moles of gas. It is not exceptionally difficult to do calculations for moles of gas. It's just ever so slightly more complicated than it would be to do a combined gas law problem. And honestly, they kind of derive from the same origin anyways, so it's just algebra, so no stress. So, first thing we need to talk about is Amedeo Avogadro. That guy, man, Avogadro's number, figuring out how many particles are in a mole of gas, that theorized number, 6.02 times 10 to the 23rd, pretty impressive. What he also theorized kind of at the same time was that under the same pressure and temperature conditions, so if I have two gases, but they're at the same pressure and the same temperature, if I have equal volumes of those gases, they are going to contain the same number of molecules as well. So the idea is generally that if I have gases that are at the same temperature and pressure and volume, I'm going to have the same amount of gas in each of those containers, which kind of makes sense. Additionally, as the number of moles of a gas go down, the volume needs to go down. And if the number of moles of gas go up, the volume expands. And all that stuff, makes a lot of sense. So what they call that law, the relationship between moles and volume, is Avogadro's law. But what I think is actually much more important is that pressure, temperature, volume, mole relationship. And so if we would take a look at standard temperature and pressure, which is STP, and I have a mole of, let's say, argon, a mole of oxygen, and a mole of nitrogen, all of them, if they are at STP, so that's 273 Kelvin and 1 atmosphere of pressure, should all occupy the same volume if I have a mole of that. That volume is 22.4 liters, and that is what we call the molar volume of a gas at STP. Now, this is a number that you're going to want to kind of like stick in the lockbox there. And remember that if you have a gas, any gas, argon, oxygen, nitrogen, carbon dioxide, carbon monoxide, whatever you want to do, at standard temperature and pressure, 1 mole of that is going to be 22.4 liters. And so if we have a gas that's at STP and you know the volume of it, you can convert easily to moles by just using that 22.4 liters. And we'll see that in our examples. But again, what I think is most important is that if let's say I don't have 22.4 liters, but let's say I do have 10 liters of each of these. So I have 10 liters of argon, 10 liters of oxygen, and 10 liters of nitrogen. I will still have the same number of moles of gas because they're at the same temperature, same pressure, and same volume. Okay, and if I wanted to figure out how many moles I had, I could use that 22.4 liters is equal to 1 mole idea to figure that out. Now, things that aren't the same for those gases. One, the density isn't the same. So in this example here, the argon is the heaviest of all the gases. So if I have the same volume but different masses, argon's going to have the highest density and then nitrogen's going to have the lowest density. Hopefully that makes sense. What will also not be the same is the speed of the particles like we talked about last time. So at the same temperature, they're going to have the same average kinetic energy, but in this case, the nitrogen is going to be the fastest because it's the lightest, and argon is going to be the slowest because it's the heaviest. But they have the same number of particles moving around in that container. And this is at STP. However, if it's not at STP, the same rule applies. We just can't use that super convenient 22.4 liters for moles conversion. And like I said, we will get into the math of that in just a minute. But if we have gases that aren't at STP and we want to figure out how many moles are in there, we need to use something called the ideal gas law. Okay, now the ideal gas law will help us figure out how many moles of a gas we have at any temperature, pressure, and volume of that gas. It will also help us figure out, if I know my number of moles, it will help me figure out any other value. So I could find the pressure if I knew how many moles of gas. Or what we do a lot in lab is we can figure out how much gas should be produced by a chemical reaction. And you can bet your bottom dollar that we're going to get back into stoichiometry. What? Okay. Very excited about that. So the ideal gas law is kind of our way to kind of get out of all of our gas quantity problems. Now, if we are dealing with a problem where we don't know the amount of gas and we don't care about the amount of gas, then we probably can use the combined gas law or a variation of that. But if I need to know how much gas is in there, like the actual number of moles or grams or something like that, ideal gas law is the ideal gas law to use. No? Okay. So, things about the ideal gas law. The ideal gas law is PV equals nRT. And our variables in here are pressure. Now, you, in theory, could use any pressure value, but my personal recommendation is whatever value of pressure you're given, get it into atmospheres. And I'll tell you why in just a minute. V, volume, right, has to be in liters for the ideal gas law. So if you're collecting milliliters of a gas, you need to do that conversion to make this work. N stands for number of moles of gas. So that N value is your moles. R is a gas constant. And we're going to get more into that in the next slide. But the R value is basically a number that doesn't change because it's a constant. And it's got obnoxious units on it. And I'll kind of show you why we use it in just a minute. Okay. The units on the gas constant that I recommend using are, it's 0.0821 for the numerical value, and then it's atmosphere, liter, per mole, Kelvin. So the R value depends on the gas pressure that you use. And that's why having the pressure in atmospheres is important, because the units for the R and the ATM have to match, okay? And then our temperature, just like all of our other gas laws, needs to be in Kelvin. So what this allows me to do is I will pretty much always have 4 of the 5 pieces of this equation, and you can use your algebra skills to solve for the 5th piece. We always have R, and then you've got 3 other variables, and you just solve. Okay, now here's the R thing. So what the R value is, it's called the universal gas constant. What it is it is the equation essentially rearranged to compare your gas to what a gas would be if it were 1 mole of that gas at standard temperature and pressure. So that 22.4 liters that I talked about, it's coming back. So what happens is, if you think about the equation as R always being your value, if it were 1 atmosphere, 1 mole of gas that had 22.4 liters of volume, and it was at 273 Kelvin, it's like comparing your gas to this known information. So it's almost like a P1, V1 kind of situation, but we always get this R value. And so the R value is calculated by taking the standard pressure, which in atmospheres is 1, and then the volume for 1 mole of gas divided by 1 mole of gas, and standard temperature, which is 273. Okay, so that's why the units change depending on the pressure you have. And you can see here in our gas constants, and this one you can ignore for now, but our gas constants, they give it to you for the atmospheres, and they also give it to you for torr. And the reason why the torr constant is so much larger is because it's 760 torr that go into our equation here instead of 1 ATM. So if you're not using atmospheres for pressure, you're going to have to get the R value to match. And honestly, I think that the pressure in atmospheres is just the easiest to use. And it's the one they use the most on the test. So that's why I do that. They also on the test give you your standard temperature and pressure. And I told you that the K value is 273.15. On the test, if you just add 273, they're not going to bug you. Also, with this constant on their answer keys, I've always seen 0.0821 for the value used, so don't stress about that 0.06. These are values that are given to you on the test, so you don't need to remember them. But the key with all of this is that all gases at the same temperature, the same volume, and the same pressure contain the same number of moles. And if you think about this equation, PV equals nRT, if I have the same pressure, volume, and temperature, and my R value is a constant number, even if I have any kind of gas, I'm still going to get the same number of moles. They ask that conceptual question a lot. They will ask that question in a bunch of different ways and try to see if you know what the heck you're talking about. So just remember, if they're at the same temperature, the same pressure, and the same volume, they have the same number of moles. Okay, so what I'm going to do is I'm going to show you guys, I had to check my time here. I'm going to show you guys 2 example problems. It's kind of like 3, but one's really short. And then I'm going to ask you guys to try them, attempt them using the information that I just gave you. Either use the molar volume of a gas at STP, or if you panic, you can always use the ideal gas law. It will always work in these situations. And then I'm going to go over answers in the next video to keep this one short. Okay, so here's the first example. How many moles of gas are in 17 liters of gas at STP? So standard temperature and pressure. Second part of this is, how does that compare to the moles in 17 liters of gas at 22 Celsius and 7 atmospheres? And I feel like that's a legit question, right? Like, if I've got this gas at STP, if I have it at different conditions, how is that going to work? So do that one. Give that a try. The other example is going to be, what is the volume of 23 grams of neon gas at 1 degree Celsius and a pressure of 2 atmospheres? All of the information that you need to solve these problems is already given in the problem. So you're either going to be using that relationship where it's 22.4 liters for a mole of gas at STP, or you're going to be using the ideal gas law. See if you can work these out, and then in the next video, I will go over the answers and give you some pointers. All right? Good luck.